Hello everyone, I'm Jennifer Bromley, Chief Scientific Officer at Vertical Future, and it's my pleasure to be with you virtually today. I want to start by thanking the organisers for inviting me to speak in this session on controlled environment agriculture, and I look forward to joining the panel later on for more discussion. I wanted to speak today about environment-led technology and operational development. And by this, I'm not referring to the controlled environment in which we're growing, but the impact that our growing practices have on the planet through their carbon emissions. At Vertical Future, our mission is to provide democratised, high-quality, nutritious food produced in vertical farms, whilst ensuring that the technology that we apply has no greater impact on the environment than current practices. But first, I'll start with an introduction to who we are. So Vertical Future is a vertical farming technology and data company. We're creating a network of green infrastructure on a global scale. We design, manufacture and install our own proprietary technologies with a staff including hardware and software engineers, operations specialists and plant scientists who all work together to ensure that our systems are optimised to the needs of the plants we are growing, rather than to attempt to shoehorn plants into an inappropriate system. Now, currently there are 8 active farms that use Vertical Future technology. There's 3 under construction and many more in the pipeline in countries around the world, including the UK, Singapore and Australia. Now, our hardware covers the full end-to-end process of indoor farming, from seed placement to harvest of crops and cleaning of used trays. As a company, we're quite unique. We started as growers using a system we purchased before making the transition to hardware specialists. We had the opportunity to learn firsthand all of the operational headaches and bottlenecks that we needed to overcome to improve productivity and scaling of systems, with a focus on crop quality and consistency. And our end-to-end solution effectively enables the crop to move through the system from seed placement to harvest without being touched by a human hand. Our lighting is 5-channel, fully variable, low wattage, low profile LED panels, and that allows us to tune the light spectrum and intensity to the needs of the crop, whilst also, and critically, minimising energy lost through heat dissipation. And that results in reduced amounts of cooling that you then need to put in to mitigate the effect of heat dissipation. We also have dual irrigation systems. We're able to install both aeroponic and hydroponic, and that allows flexibility to the needs of the crop, both by crop and also by the age of the crop. Now, commercial vertical farming is currently most associated with fast-growing leaf crops, including baby leaves, herbs and microgreens. And when we look at the unit economics of lettuce, you can see how the case really starts to add up when you compare it to open field and glasshouse production, both in terms of resource use efficiency, so when you look at the fertilisers and the water that's used, and also in terms of the productivity per unit area of land, effectively through hyper-intensification, which you get in vertical farming through the addition of many levels of growing. Now, the opportunity to produce close to the site of consumption also reduces the transport miles associated with the crop. And from an economic standpoint, these are all cost savers, and that's great, but they also, and very importantly, provide an environmental benefit through reduced emissions and also through reduced impact on the environment through fertiliser leaching and water abstraction. But how do we assess the viability of a crop and the technology being applied beyond simple unit economics to drive technology and operational development? At Vertical Future, we use a process called Lifecycle Assessment. Now, for those unfamiliar, Lifecycle Assessment is a process which maps the environmental footprint of a product. And this goes from the extraction of the raw materials used in manufacture, both of hardware and consumables, all the way through to transport and waste. So this looks at the whole supply chain involved in the vertical farming system. Now, LCAs have been successfully implemented in decision-making processes, both by companies, by consumers, governments, NGOs. All sorts of different organisations use these as data-driven drivers. And we see that as a key advantage because it gives us a data-driven roadmap of opportunities to improve the environmental performance of our product. And this can be as simple as sourcing differently. Now, for example, our steel that we source to fabricate our systems, we can look at which steel mills we're sourcing from and the efficiency of the operation of those steel mills. but also through things like applying a different manufacture process or developing less impactful operational processes once the technology has been deployed. Now, the method for carrying out an LCA is codified by the International Standards Organization, which you may have heard of, called ISO. And that allows us also to pull information from other LCAs in the sector and make honest comparisons between our life cycle analysis and other life cycle analyses that have been published. And one of the areas that's codified within the ISO standards is peer review and publication of that LCA. So there are 4 phases for an LCA when following these standards. The first is goal and scope definition. Essentially, what do you want to achieve and what are you looking at in terms of the size of your life cycle? The inventory analysis, that's data gathering, just going out, looking and getting the data. So the best data that you can gather is direct from the manufacturer or the raw material provider. If you're not able to get that, you can get it from inventories that are available. And if you can't do that, you can derive it from elsewhere and you can look in published materials, etc. The next stage is carrying out the life cycle assessment, putting all that data together and looking at what the embodied carbon looks like. And then the final is looking at the interpretation. So that's the looking at which parts of the system are having the most impact, and then looking at how we can stress test that through changing different aspects of the system. So looking at different sourcing activities or looking at different energy inputs, for example. So this diagram here shows the system and the scope that we're assessing. Essentially, in our life cycle assessment, we're looking at the materials and manufacturing and decommissioning of our systems, which is all shown in the left-hand boxes. And this decommissioning follows a 20-year period of operation, which is shown in the crop life cycle to the right. And you can see within the crop life cycle, there are certain areas that are out of scope. We've decided to end our analysis at the distribution hub gate for crops, since we can reasonably assume that this will be the same for all growing systems. So once you get your crop to the distribution hub, whether you've grown it in an open field, whether you've grown it in a vertical farm, essentially the downstream treatment is going to be the same. And the different boxes going downwards reflect the different stages in the life cycle of the infrastructure and crop. So we've got upstream, we've got farm operation, we've got the downstream, and we've got the end of life. And the downstream and the end of life only really apply to the farm life cycle rather than the crop life cycle. And because we're conducting a comparative LCA, what we did was we took the scope of the study and defined it to ensure it matched with the scope of a previously published open field life cycle assessment. Specifically, we chose one that was published in 2007 by the University of Surrey. And this is the only published study which includes a UK, a EU and a non-EU site, which are particularly common growing locations for crops adopted by vertical farms. So looking at the size of our analysis, we modelled a 9,600 metre square vertical future facility, which we chose to locate within a logistics distribution hub in the UK. And we chose this location. It's logical for large-scale vertical farming to be co-located with supply chain logistics. Given the farm doesn't have to be located in an environment suitable for the crop, working with the needs of the food logistics provides an opportunity to improve product quality in the hands of the consumer by shortening and simplifying supply chain structures. Now, I mentioned earlier that the system boundary, we stopped this at the logistics gate. And it's assumed that the downstream emissions for open field and vertically farmed processes are the same as transport post-distribution warehouse, will be the same no matter what the method of production. However, what we haven't been able to account for here is the impact of the crop in the system prior to being in the hands of the consumer, and the impact on post-harvest waste through transport and reduced shelf life. Now, I've listed here as well the production and counterfactual scenarios that we selected based on the market the vertical future is working in and also available data. So we looked at 3 scenarios. We looked at a year-round import of butterhead lettuce from Murcia in Spain. We looked at a mixed model of UK-based production for 4 months of the year and 8 months of the year in Spain. And we also looked at basil production in the UK, Spain and Uganda. We've also modelled a number of different energy use scenarios as we see energy supply rapidly changing by its source around the globe. And this is typified by the UK national grid, which is shifting to renewables. This will have a massive impact on the carbon emissions associated with CEA when compared to other production methods. So in the UK, the renewables in the grid has been modelled on a 2022 breakdown. So we've got 70% wind, 15% solar, 10% biomass, 10% hydro and other. But also worth noting is that the UK also imports a sizable chunk of energy. And as France is our main source of energy inputs, we've also used the current French grid mix to model this. But a producer doesn't have to accept the standard grid mix. It's also possible to enter into power purchase agreements where a specific type of energy is used. And a physical power purchase agreement provides an additional granularity by accessing energy produced directly at a physical site. And these physical PPAs avoid accounting issues in our analysis by knowing exactly where the energy has come from. And so here we've also modelled PPAs from wind and solar farms. And so here I've shown a plot incorporating data from published life cycle analyses, all focused on the embodied carbon in 1 kilo of lettuce. So in light blue are published LCAs showing the embodied carbon values for open field production in the UK, the EU and wider global data. The dark blue shows various analyses that look at production in vertical farms, which are grouped by energy source. And the green bars show the 4 energy scenarios that I just spoke about, modelled for vertical future facility operation. Now, as you can see, when we look at grid mix, vertical future facilities outperform published LCAs in other vertical farms, whether you're using the eco-invent grid or whether you're using the modelled grid mix, and they're broadly comparable in scale to other analyses that looked at wind and solar as the energy source. And in this, I also include the Scottish grid analysis here because the majority of Scottish power is wind derived. So from this isn't our last point in our life cycle assessment. Our next steps here are to remodel the data from open field analyses with the modelled grid mix in order to carry out a fairer comparison, since the key comparator study that we've been using here is now 15 years old. And so in 15 years, the grid mix has changed quite massively, and so the data that we're pulling in might not be exactly comparable. We also want to add in soil emissions to the open field analyses, since these have recently been updated using data collected from drained arable land in East Anglia, which shows the carbon emissions from drained soil. What it also tells us, though, is that we have got some work to do to improve the performance when we look at the embodied carbon per kilo of produce in our vertical future systems, and also vertical farming as a whole. When we look at the process contributions, this Sankey plot shows the contributions of the various processes into the total embodied carbon. The left of the plot shows the system manufacture, which contributes 18.4% of the embodied carbon, and the right-hand side of the plot shows system operation over a period of 20 years, which embodies over 80% of the carbon in the kilo of lettuce. And there are gains to be had on both sides. 64% of the embodied carbon in system manufacture actually comes from one element, which is the LED printed circuit boards. And so this is an obvious target for innovation and a move towards modularised LEDs with greater opportunity for repair and recycling. In terms of operation, published life cycle assessments agree with ours that energy used in operation of vertical farms is the greatest contributor to embodied carbon in the crop. And so this is a huge opportunity for innovation, both technical and operational. So if we look at renewables, for example, they significantly reduce the impact. So in Vertical Future, we incorporate renewable sources of energy, such as air source heat pumps, into our climate management systems, which are highly efficient means of providing cooling and or heating into a system. In the scenario here on the published assessment I'm showing you from Blom et al., the electrification of heating with a ground source heat pump combined with steam production and an electric boiler, electricity production with photovoltaic panels were considered the most effective means of heating and cooling. And when they looked at the core emissions in vertical farming, it reduced by 83% in their sensitivity analysis post LCA. And this LCA, just for sort of full disclosure, was based on the Netherlands grid mix in 2022. But beyond technology change, how can you reduce the energy to grow crops without impacting on the quality? And this is a key area that the research team at Vertical Future look at. And quite simply, light is a key target. In vertical farming systems, they use typically more than 50% of the energy requirements. And as our lights at Vertical Future are fully tunable across 5 channels, this gives us an awful lot of scope to play with. As an example, red light uses less energy per unit than blue light. And so altering the balance of red-blue can have massive efficiency gains, can also have huge impacts on the phenotype of the plant though. And so that's where we really do have to focus on quality at the same time. So here's some data from a recent study that we carried out at Vertical Future. So we look at 2 stages of the growing cycle, establishment and onward growth, and the light intensity provided in each of these stages and how it impacted the fresh mass of the crop. And so what you can see from the graph that shows establishment is essentially during the first 10 to 12 days of crop growth, there was really no difference in the mass per plant. And so really what that's telling us there is very little light intensity is required in that early seedling establishment. However, you do get to an inflection point where the impact of light intensity has a huge impact on the mass per plant. And so at that point, we looked at we're calling onward growth. And then we looked at different light intensities again. And during these, we saw a plateau in intensity. And this was a study, again, in lettuce. And that plateau, we saw no significant yield increases after that plateau. So what that told us is a combination of the lower seedling establishment combined with a mid-range lighting solution is the ideal combination in terms of yield. And this recipe resulted in 30.5% less energy used to grow the plants. But this was also accompanied by a 13.6% reduction in yield. However, that yield reduction isn't the end of the world, because when you look at the efficiency of this recipe, it's at 124% of the typical lighting recipe used for lettuce. This also, when we look at the carbon embodiments, reduces the embodied carbon in a kilo of crop by 150 grams per kilo. And if you're thinking economically, this recipe results in 22.4 kilowatts saved per metre square per year. And over a 9,600 metre square farm that we modelled, this equates to almost £80,000 in cost savings. We also noted as well that the variation in yield was smaller, meaning that the production is much, much more predictable, enabling better crop planning and much more efficient and effective system use. And with that, I think my 20 minutes has almost come to an end. I'd particularly like to acknowledge the work of Tom and Felipe, who I have carefully drawn a box around in this picture. Tom drove the LCA, and Felipe was instrumental in developing the light recipe that we presented here. Now, this isn't the end of what we're doing at Vertical Future. There's so much more still to do, and I really do firmly believe that we can only improve things further. Thank you for listening, and I look forward to the panel discussion later.